So this formula is always true. Will there always be an intersection? If I said, let's probably get a rock or an ice cream cone, there are no that I know of. I always got to be careful because I used to use cats and dogs. And then there was some stupid cat-dog cartoon.
Stop this, man.
Dude.
That last class.
Huh?
You weren't even here last class.
Exactly. Well, you just know what happened, right? You just felt it. Let me see. All right, so we still have to fill this in right here. So, and basically means multiply, or basically means add, with one little adjustment. This is going to have an adjustment here for when they're not independent. I like it. And it kind of makes sense because I put it like this before, right? When I said I went to the financial aid book, this giant book, before we had the whole internet. And we had to look through and we had to read through. You have to be this and this and this. So the number of people that matched it got smaller and smaller and smaller. Does anybody know what happens when you multiply two numbers that are smaller than 1? What happens to the result? Like what's 1/2 times 1/2? They get smaller, exactly. So it makes sense that the and, which is more restrictive, will be based on multiplication because that will always make the result smaller. Or is based on addition, that's going to make the result bigger. It's going to incorporate more and more people. Right? It's like the nice bouncer. You can be rich or good looking or have a nice car. Any of those you can come in the club, right?
But this is different than what you were going over before of like getting a blue, then another blue. You're talking about...
No, this is exactly that. Because getting a blue and then another blue. Yeah, so when you write this kind of thing down, the and is hidden. Because this does mean blue and then blue. Cool.
But you could do it for like 2 qualifiers, right? As well? It's the same formula. Like, what's the probability you get a woman and a woman that said no as one choice but 2 qualifiers?
If you, well, all right. So if you said like, what'd you say? Probably a woman
I guess.
and a woman who said no. Well, that would just be the women who said no.
Right.
Yeah.
Okay.
Yeah. But I see where you're trying to go. Something like that could happen, but not yet. Not for us. I like it. Okay. Let me see. So last thing today, I think, is going to take us a little bit, is to fill in what happens here when I have something that's not independent. And we sort of already did this too. And of course, I already erased my poor little chart. It's just easier to see in chart form what happens here. What was this again?
3, 7, 3, 2.
All right, cool. Just use the same numbers again. So, continuing off this string, wherever I left off, I can't remember my Roman numeral. What's the probability I get a woman given the person said yes? So we've already talked about this idea of given before. So that sounds like what we need, because why would this change? Because given that A happened, given that I already picked a red chip, what's the probability now that I get a blue chip? So that's the kind of thing I need to develop a formula for.
2/9.
Yeah, so what's the bottom going to be now?
Just the wing.
No, what is it that I know about this person? What's the probability that they're a woman? Given that they said yes. So what do I know about this person? They said yes, so what goes on the bottom? 9. Cool. I like it. Make sure we're in the right direction for the right reason. Now, only somebody out of those 9 could have happened. Does that make, it's a weird way to say it, but does that make sense? Right? Somebody who said yes has to be what I'm talking about here. So out of these 9 people, how many match what I'm looking for? 2. All right, let's try to piece together what this formula is then. So in chart form, it's easy to kind of calculate all the probabilities, and then I can step back and say, well, what must the general formula be based on what the hell we just did? So that 9, so let's develop A given B. What was that 9 related to? Yeah, the part that was given. So on the bottom here, it's going to go related to the part that was given, right? So let me see if you guys can handle this. So given B, so on the bottom goes basically how many are in B. What was this number now? How would you define these people?
A.
They are, define them in English, like
Women that said yes.
they are women and somebody who said yes, right? So this would be, they had to be women and said yes. So this has to be A and B. So that's the formula for given. And we call this a conditional probability. On the condition that this happened, what happens to this probability? So we call this a conditional probability. I like it. And this is the one that we use all the time. Given that it is going to be 4:45 when I hit the road, I'm probably going to change the route that I take to go home, right? Because I live that way, and the stupid 125 sucks when you try to go, oh, well, screw it. You guys kind of, we use this kind of thing all the time. We just don't think about it in that sense. So now I have a better idea of what to do here. If these two things are independent, what should happen? So if, I keep wanting to erase that, and then I don't want to. If A and B are independent, you can spell it. Independent. One more D. I love the word, it's like the banana. Independent. If A and B are independent, then what should happen here? If B happens, should A care?
No.
If they're independent, B happening should not change. So like, if I put the chip back in, I get a red one. Is it going to affect the probability I get a red one again? No, because I put the damn thing back in. They don't care about each other. That's why the word independent is a nice word to use. So this, if they are independent, this must be true. Given that B happened, will A change? No. Maybe. Let that make sense? If they are independent, they don't care about each other. So if B happens, A's probability stays the same as it was. So that's what the word independent means. They don't care about it. They don't affect each other. I like it. So that's why this formula is the way it is. They don't affect you. They're separate. They don't have any mixture of each other. So here's what's going to happen. Here's the neat thing. So here's our little tiny bit of algebra that sneaks into this class. I have a way to get a formula for A and B. It's right there in front of me. How do I solve that equation for the probability of A and B? What do I do? How do I solve for this?
Probably A times.
How do I do that? Do what to both sides? So how do I solve this for X? Multiply by 5. I love it, because you want to kill the thing that's being divided. So how do I solve this for A and B? Multiply by probability of B. So I get probability of A and B equals the probability of B times the probability of A given B. Or I could do it like this. Both of these are the same. Now think back to how this worked with our red and blue poker chips. When I didn't put that second one back in, it was, the probability of red was 4 out of 10 times the probability of red given that I already picked a red. So that's why the second one changed to 3 out of 9. It was a given. Given that I already picked a red, the second guy changed. I like it. So that is the official formula for and. Makes sense. What did I just say about if they're independent? What must be true about this? It's got to equal that. And what should this equal? Just to make this a complete picture. Probability B. So if A happens, B doesn't care. If B happens, A doesn't care. So this formula we created from the tree. It made physical sense. This formula made physical sense. That one is a little less because we use some algebra to get it, so students tend to trust it a little bit less. But look at the connection now. If A and B are independent, what is this? So it'd be PA times PB, which is what this says. Right? The same thing here. Same thing. PA times PB, which is what this guy says. That's if they're independent, you just multiply the two together. Exacts. So I know right now you're all worried about what the hell is this going to look like in a problem, right? All right.
You mean that you did prove for that formula? You proved it right now?
I did. I so did. Because if you are cool with this, and I think we are, because we've done givens before today, and this is just writing what we did. So if this equation is true, that's the power of algebra. If you write down an equation that's true, you can manipulate it with algebra. That's where algebra comes in. So I know this equation is true. We've seen it a couple times. So I know this must be true. Because that was just using algebra. I like it. I like it. Let's see. Oh, I got a little bit of time.
Wouldn't the b's just cancel out? And it just be the probability beta?
Where are we looking?
At the very bottom, the conditional probability.
You gotta be careful. This is not, the top is not this. If it was this, then they would cancel.
Okay.
Yeah. So you can't like break into that.
Right, so it's respective of each other.
Exactly. So that's its own thing, and that's its own thing. Cool. They are related. I like it. I like it. Maybe. So let's do a concrete example real quick. It's going to be a little less.
But then you contradict yourself right there, because it is the same thing, right?
When is this true? When is this true?
If they're independent.
If they're independent. When is this true? Always.
Okay.
So this is the more general analog to this, right? Specifically, when they're independent, this equals the probability of B, and I reclaim this
Right.
in that specific case.
Only if they're independent.
Only if they're
But
independent.
you,
I like
that'll count if they're not, if they're dependent as well. Got it.
Yeah, this guy handles every situation. Kick ass. All right. So let's see a little specific, concrete example. What if you knew that the probability of C was 0.7, the probability of C and D was 0.5. So this is an example. If I give you a chart, that's awesome, because then you can just count everything you need. If I don't give you a chart, I just give you probabilities, that's really the only time you have to rely on the formulas. In the chart, that's how I made the formulas. We did the work, and then we made the formulas from what we did. We don't even need the formulas to answer the question if I give you all the numbers. If I just give you probabilities, oh shit, I got nothing to count. I got stuff just to plug in. So I tell you that they're independent, which means what? What does this formula become then? Well, let me put this C and D. Probably C.
Times the probability.
So I can write this because of this. And now what can I do with these? Plug and chug. So that feels sort of like algebra, but it's, easy algebra. So where's the 0.7 go?
The probability C.
Right there.
And then 0.5 on the other end.
Right there. And then how do I solve for P and D?
Divided by 0.5.
Divided by. So there's a whole little section in the homework that just gives you numbers. And they might give you a situation, so you have to use the right formula and just plug and chug. Let that be nice. Right? That's kind of nice. So what do you get there?
0.5 over 0.7.
Yeah, whatever 5 over 7 is. Whatever that is.
49,
Something like that. Yeah. It'll be...
49, 1.
No. It'll be more than that. What'll it be, Jeff?
It's 50.
What'll it be?
By 7, it's 7, I'm sorry.
Yeah, yeah.
0.70.
70 something, right? 72.
714.
Okay, thank you. I was going to see how long it would take it, so I pulled out a calculator and save this. All right. So there's a whole section like this. There's sections that give you the chart. The chart's nice because you don't have to use the formulas. One last idea. Let me see. I'm gonna be taking a risk here. Let's see what happens. Out of a deck of cards, I just have to use cards at some point. What's the probability I pick out? If I pick one card, what's probably I pick out an ace or a club? Let me see if you guys get this.
14 out of 52.
So if you don't really know cards, you know that there's 52 cards.
16 out of 52.
52 cards. 4 suits. Right? There's hearts, diamonds, spades, and clubs.
How many total?
So it's 13 in each suit. Right.
16 over 52.
So how many aces are there in a deck of cards?
4.
4. How many clubs are there? 13.
Minus.
But what do I have to be careful about?
Because there's an ace that is a club.
There's an ace of clubs, so I got to subtract that guy off. So when I add 4 aces to 13 clubs, I added the ace of clubs twice. Over 52. Cool. 16 out of 52. 4 out of 13. Cool. And then whatever that is. All right. So if you want to, this is the work you're going to show me, by the way. On this kind of problem, this is the work. You can write your answer as a percentage or a decimal, I don't care. As long as you show me the fraction work that went into it. If you just give me the answer and you made a mistake, I don't know what the hell happened. So what's the difference here? What if I say what's probably like an ace or an 8?
They're not going to overlap.
They're not going to overlap. So if I have 4 aces, and how many aces do I have? 4 out of... Why wouldn't I subtract anything? Because there's none of them that are both, of course. They don't overlap. So we... Good.
I was just going to ask, if we just assume the subtraction, I show like 3 plus 13. Is that enough? That's just for showing work.
Oh, well, 3 plus 13 would be great work. That's fine. If you don't double count in the first place, you got less to write. So I would call the ace and 8, I would call those mutually exclusive events. Mutually exclusive events. Kind of makes sense because exclusive means I only let certain people in, or things, or whatever. And mutually exclusive means I don't let you in, you don't let me in. So no 8 aces can be 8s. No 8s can be aces. Mutually exclusive, which means there's none that can be both. I like it. Kick ass. So it's sort of like an analogous idea to independent in a way. I shouldn't even have said that. Because mutually exclusive and independent are not the same thing, but they sort of deal with the same idea. Cool. So when you see these terms, independent, mutual exclusive, you know what they mean. If I said that event F and event H are mutually exclusive, what do I know is true?
They'll never overlap.
I like it, but what probability statement can I write? Here's the thing. I want to see who can tease this out. If they don't overlap, then what can't happen? Whatever F is, whatever H is. How many things are F and H?
2, 1.
None. Isn't that the idea? That's mutually exclusive. You can't be both. So what's the probability of F and H?
0.
0. Always. Any 2 things that are mutually exclusive, the probability of one and the other is 0. That is the probability definition of mutually exclusive. I like it. Cool. I think that's plenty. So just to let you know, next class, we got the quiz, and then I got a little handout with all the probability stuff we've done so far, exactly the way it would look like on a test. So a little review.
Wait, what did I say?
The next test is the 16th.
Is that the last?
So a week from next Monday. We're like less than 3 weeks away from the final. I don't know if you guys know that. Finals on the 18th, I think. Don't hold me to that. 23rd,
18th of May.
23rd.
Of May.
Yeah, dude, of May.
Cumulative?
Yeah, cumulative.